and known all of them, been friends with them, worked with them, and or watched them work for over 25 years. And in many ways, they've shaped the Earth system science at NASA as it exists today. And so we're really fortunate. Our first speaker, Dr. Sellers from NASA, is not only well known for his contributions in climate science and Earth observations, but as many of you know, he's also an astronaut 3 times. So how amazing is that? I think, you know, all of us kind of see ourselves as astronauts through Dr. Sellers. He's an incredibly busy man, and we're really, truly lucky to have him speak to us this morning. Dr. Sellers?
Thanks, Ron. How's everybody doing? Did you all hear me okay?
Good. Yeah.
Yeah.
Yes. Looking for twitches around the table. All right, very good. Okay, well, let's see. Rama asked me to talk about, I don't know, how you guys and how we all fit into the business, the big picture of big science, I guess, the challenges that are out there ahead of us, and the contributions that this community, and that means you lot, because you guys are going to do the work, Ram and I and Ranga are probably past it. I don't know. What do you think, Ranga? Yeah, he's not answering, so he probably is. I can't hear you guys.
Can you hear us?
I can hear you now. You didn't respond. No, I'm looking at the younger generation around the table here, and I'm figuring that they're the people who are going to have to carry the load for the next 20 years, no matter how healthy our lifestyles are, Ranga.
That is
What do you
true.
think? That is
agree.
true. So, okay, so here's a picture. You can see a picture of me hanging off the space station. This is the way to do remote sensing that's a lot more fun than most ways we do it. But really, that's not the practical way to do business. What are we really about as a community? And I think this is, you know, in broad terms, this is the challenge that's ahead of us. The whole business of global change, the whole business of trying to improve global models, use satellite data, and then where do you fit in? Where as scientists do we fit in to make things better, to you know, do good science and have fun? Well, you guys are in a terrific position to do a lot of good. Global change is accelerating, and I think that, you know, in spite of setbacks politically and all the rest of it, there'll be continuing interest, demand for information, demand for ideas, demands for better predictive tools, all those kinds of things from the public and politicians. So I think you guys are going to be in a seller's market. I really do. What's really interesting right now, as you all know, is what's happening in the Arctic. That the Arctic Boreal Zone is the fleet leader of global change right now. It's warming twice as fast as anywhere else on the planet. We think that's mainly due to the ice albedo amplification effect, among other things, and that seems to be the main factor. And we're seeing remote sensing tools being employed really across the board to tackle this in a way that wasn't done for environmental problems 20 years ago. So this is exciting stuff. But some things don't change. The models still need to be improved. We don't have the predictive ability that we would like. We are a lot better off than we were 20 years ago, and I'm going to talk about what it was like 20 years ago, or 25 years ago, when we started out in the business, to see how far we've come. But I'm hoping that your generation will basically take it another huge step forward during your careers. So the models need improvement. We've got to maximally exploit the satellite data to make the models perform better, to initialize them, to validate them, prove them across the board. And we'll always need a field experiments to make sure that the models are really truthful and the satellite data algorithms actually work. So in short, you guys can save the world if you manage to accomplish all this stuff. So I'm going to kind of rewind through a little personal history to let you see how far we've come and also give you an idea of what it's like as an individual scientist or a group of scientists to tackle a big issue like this and try and make progress over a period of several years. Okay, and I'm going to talk about 2 experiments, the Pfeiffer and Boreas experiments, why we did them, and what we got out of them. It's actually been 25 years since 587, but this is an old slide. And it's interesting, how do we start this business, and what motivated us to do all this work? Millions of dollars, hundreds of man-years plowed into these efforts. And I'll define what FIFO and bull race are in a minute, okay, in particular. It already started in 1981 with a workshop, which I didn't go to, which is on land surface parameterizations as used in atmospheric general circulation models. And they invited a whole lot of hydrologists, meteorologists, and satellite people to Goddard, and they had a little conference, and they concluded that the models of land surface parameterizations as used in climate models were terrible. All the climate models had these fixed fields of albedo. Often they didn't vary seasonally, they were just fixed around the world. The poles were white, and everything else was a kind of a dull gray. Surface roughness was made up, usually was one value for all the continents. There was a one-dimensional soil block model for heat transfer. There was the so-called beta function for evapotranspiration calculations, and vegetation wasn't there at all. It really wasn't featured at all in any of these early models. But I think that this group asked a very good basic question. Is it worth improving this stuff? What's the benefit? Why bother? And I'm going to go quickly to this slide. A couple of friends of mine at the time, Schuckler and Mintz, decided to see, really, does it make a difference how you treat the land in these global climate models? And what they did was they got a very primitive climate model at the time. It was 4 by 5 degrees resolution, and I think only about 12 layers in the vertical. It was pretty primitive, but they did a very simple experiment. They basically allowed the land surface to be completely wet in one case, like a paddy field, okay, worldwide, and in another case, it was like a parking lot. It was bone dry, no matter how much rain fell on it. It was immediately, all the water drained off, and it was bone dry. So it was a completely free evaporating case in the wet soil case, and a dry, no evaporation in the dry soil case. Now here's the wet soil case, and you can see, looking at the blue contours, is everything higher than a couple of millimeters a day of rainfall. And you can see there's a lot of rainfall over the continents, particularly the northern continents. Right in the interiors there, it's more rain than is actually present over the continents. But don't forget that in this case, they pretended the wet soil stayed wet no matter what. They had a fantastic global sprinkler system or something installed. And so what's happening here is that the water evaporating from the surface is getting into the hydrological cycle. It's forming clouds, and it's raining or re-raining over the continents. So the rainfall that's falling over the land here is in large part recirculated water that's been evaporated up. Now, fix that on your retinas, and let's go and have a look at the next pic, which was the dry soil case. So with no evaporation, basically the continental interior is dried up, except for areas where it's transported in along the intertropical convergence zone or the monsoon zone over India. So in the absence of large-scale advection from the oceans, continents pretty much dried out. So this is conclusive proof that it does matter, and if you're going to say anything sensible about climate and climate models, you better pay attention and do a better job of modeling the land. So that was inspirational, and these guys did this in 1982, which is like a year after that 1981 conference I was talking about. I'm going to go back a couple of slides, because I can, and just look at the state of the art as it was back then and shortly afterwards. So the Schuckler and Mintz experiment showed drastic differences in precip in continental interiors as a function of the wetness of the land surface. Charney did this nice experiment where he showed that changes in the albedo of the desert changed the Saharan climate, particularly the amount of rainfall falling in the Sahara. And his thesis was that desertification actually breeds more drying. It feeds on itself. So that the reflected radiation prevents, if you like, more convergence and the bringing in of moisture from the oceans. And roughness, Yogi Su did an experiment where he showed that changes in surface roughness, which is a function of vegetation, could have quite an impact on precipitation rates in continents. So, at the time, this is 1981, people concluded it'd be great to do a better job in models. It would be good for weather prediction, and it would be good for climate models. Meanwhile, at the same time, the discussion about global warming was just beginning. Jim Hansen had published his papers in the late 70s, 79 or so, and the first real global warming studies were coming out 79, 80, 81. So all this stuff is happening at once, and all eyes are on the models to do better. So, in the nick of time, here we are. And so, this long acronym, ISLSCIP was born, International Satellite Land Surface Climatology Project. It took us a little while to get our first meetings together in '84, but we decided in those first meetings it'd be good to do some field experiments to figure out how we can improve land surface parameterizations in models, and also, because we're NASA, develop satellite-based methods to initialize and validate these models on large scales. So 2 tasks within one set of field experiments. Most of the heavy lifting was done within Goddard, but we had a lot of friends all over the country who really helped out with the science. In 1986, there was a little experiment in France, which we piggybacked on, got to see how they did business. And then in 1987, we got to Manhattan, Kansas. Everyone knew we were serious about doing science if we were going to go to Kansas rather than Honolulu or somewhere like that. So there we were. And I show these pictures of the science plan because in those days we didn't have computer graphics, and so these are nice hand-drawn pictures of airplanes that I did, and little wind roses and things. This is the way we did business. Mom and pop shop, and even the underlines we did with a felt tip pen. Oh, it's very nice. Cottage industry. So, to give you an idea of the level of effort involved in this, we got together through the proposal, the AO process, announcement of opportunity process. We put together a science team to do this, and in most cases, these were people who had never worked with each other before. And when I say hadn't worked with each other before, not just, me and Fred, my friend next door, working together. They had not worked as communities together. They never even went to the same meetings. They didn't even know of each other's work. They didn't read each other's papers. These were like isolated communities. Atmospheric boundary layer were the people who were interested in how heat and moisture affects the growth of the boundary layer, cloud development, things like that. Surface fluxes, this was a bunch of people who knew how to measure the fluxes of radiation, heat, and very, very early stages, carbon dioxide from the surface. Correction calibration, that was the business of satellite instrument validation and airborne instrument validation. Surface radiances in biology. These are the first people looking at reflectances from the surface, leaf properties, vegetation index, all that stuff. Soil moisture, a whole bunch of people doing that using both in situ measurements and microwave remote sensing. And then a few integrative sciences who are hopefully going to pull it all together in models. So 35 teams altogether, and about 100 people, 80 to 100 people, depending how you count them. And I'm not kidding, the first meeting everyone had, we almost needed an interpreter. Everyone was using different units. They had no idea what each other was talking about. It was quite the thrash. But this was the kind of activity we ended up with. We had a 15 by 15 kilometer square in the middle of Kansas, near Manhattan, the so-called Little Apple. And this was large enough to be very visible from orbit using AVHRR data, which is 1 kilometer pixels. So you've got plenty of pixels in there from orbit, you can locate yourself. But also it's small enough to be practicably measurable using surface and airborne equipment. I mean, you could walk around it in a day if you were very fit. You could have some practical, hope of being able to quantify what's going on over a 15 by 15 kilometer square. Well, that's the way we felt at the time. So going from the surface, we had all these surface sites, measuring surface fluxes and radiances. Then we had a helicopter, which basically checked to see what those surface sites looked like at the sort of 10 to 50 meter footprint. We had a couple of low-flying flux aircraft, which would zip up and down 20 foot above the surface, and they were measuring fluxes of heat, water, and in one case carbon dioxide from the surface to the atmosphere. We had a C-130 that was equipped basically like had a Landsat emulator on it and a couple of other instruments. And then last of all, we had the satellites, Spot, Landsat, GOES, all those things. There weren't that many back then, and AVHRR on the NOAA platforms. And we tried to make sure that our aircraft were flying over the site every time the satellite came over and the weather was good. So all in all, quite a lot of coordination. You try and get all these people measuring the same thing at the same time in roughly the same place. At the same time, you're acquiring satellite data. And then you go and drag it all off to your cave and analyze it. Early results, very encouraging. These are images put together from one of the low-flying flux aircraft of the 15 by 15 kilometer area. And if you look at the one on the top left, you can see a greenness index, and that was just from a little visible near-IR radiometer stuck underneath the aircraft. So, just basically putting those data together over the area. And see how well that correlates, that pattern of greenness. See how well it correlates with CO2 flux, with the temperature difference. The warm areas the warm, hot areas are less green, and they're giving you less CO2 flux, less photosynthesis, and also less evaporation. And you can see the correlations very encouraging between all these different things. That's just a preliminary look at the data. And we, basically beat the data to death in many different forms. Digital elevation model combined with simple ratio data, combined with microwave surface soil moisture data here, and then airborne eddy correlation measurements over the same areas. This is a stripe taken down through the 15-kilometer site. So we began to see these correlations very strongly from the get-go at all scales. And it was very encouraging to see how the models that worked pretty well at the sort of site scale of a few tens of meters that all the surface flux people were happy working at, that with some tricks, you could scale them up to calculate fluxes over the 15 by 15 kilometer area using remote sensing data to spread the surface condition around. So it was very encouraging. We were so encouraged, we decided to do it somewhere more difficult. So off we all went to Canada. And the reason we went to Canada was that the global models at the time, and this is actually Jim Hansen's model, are run in I think this was like in the mid-80s. The prediction even then was that the first wave of global warming would happen in the northern continental interiors and closer to the pole rather than to the temperate zone. So we saw this sort of hot spot developing in the middle of the country, okay, or rather the middle of the continent, and also the polar warming as well. So we thought, okay, we want to be where the action is. Let's go where the global warming is first indicated to occur, and then do our next land surface experiment there. By that time, the community was now a lot more used to working together. And so we had ecologists and people who were interested in biophysics, the albedo, roughness, surface energy balance, and all those things, all working together and trying to connect the dots and use the satellite data and their wisdom to calculate heat map fluxes to the physical climate system, and maybe even look at carbon dioxide and methane release. So this is way back there in the about 1990. When this picture was put together, and it still stands up today as a sort of framework to try and figure out how to model these things on a large scale, and how to take the knowledge you get from local scale tests and experiments, and move that up to the point where you can apply it in a global model. okay, the forest is bigger, the scope of the experiment was bigger, so we had more people. By the time we were done, we had 6 teams again, but all in all, we had 80 plus principal investigators, each with their gaggle of postdocs and students and whatnot. So by the time we were done, we had a science team that was pushing sort of 250 to 300, depending on when you snapshotted it. And a lot of them are still around. Boris was a lot tougher than doing the experiment in Kansas. And it was tougher, but so were we. Having been through the Kansas experiment, we learned a lot about how to manage these things, about what was important, who worked well together, and so on and so forth. And so we went into this business with our eyes open and in pretty good shape, whereas going into the Kansas experiment was a learning experience every day. For example, it was a full-up joint US-Canadian project with some other people joining in, but mainly Canadians put up about 1/3 of the resources. We put up 2/3. So that was great to share the burden there. We had 2 study areas. They were separated by 600 kilometers. So that was a logistical challenge. But when you look at the scope of operations in the mid-90s, when we were doing the bulk of the field work, we had 12 aircraft. We had a million square kilometers within the experimental region, 12 towers, and I'll show you a picture. When I say tower, I mean a real tower now, really huge thing, about 300 people. A lot to deal with in terms of logistics, communications, and operations, but all of that actually worked out quite smoothly in the end. It was a rough place to work. I thought that Canada would be just this idyllic place where we'd all wear check shirts and walk around singing the lumberjack song and things, but actually it's much harder working there than in the middle of the Amazon. There are bugs there that will just eat you alive, and that's why nobody lives in northern Canada and Siberia except for the people who have to. Canada took over the infrastructure, and work at some of these sites still continues. This is a picture. Wow, look at that. Way back when. Site reconnaissance. Yeah, Forrest Hall, who looks the same. Andy Black, known as 3 Bagger Black, because he would fill 3 bags every time we went flying looking for sites. And myself, navigator, pilot, and airborne ecologist, and we flew around in this thing, finding all the sites that we needed. And the scheme for doing this kind of work had evolved significantly from Fife, and through discussions and thinking, talking to lots of smart people. And this is the framework that's basically was used in Boris and has been co-opted by many experiments since then as a reasonable hierarchical approach to the problem. There's process study sites where you have people who are familiar with doing studies on the leaf scale or the plot scale, measuring fluxes of methane, for example, with little chambers, or looking at leaf radiances with radiometers. Those were embedded within an area that you had a flux tower, and these flux towers would stick usually about 5-10 meters above the canopy to measure, with eddy correlation, measure what's coming off this larger area, about one kilometer typically. You have a group of these flux towers in a sub-area about 40 by 40 kilometers, which we hope to use as a modeling framework. We collect very detailed remote sensing data over that area using airborne platforms to allow us to map what's going on, and then correlate our calculated fluxes with airborne eddy correlation, which you can use to cover this whole 40 by 40 kilometer area, no problem. Study area was a bit larger, had more extensive data, hydrological data, and all the rest of it. And then the region, which we were studying, was about 1,000 by 1,000 kilometers, and for that region we collected as much satellite data as we could, wall to wall, and did a few airborne transects of things where we saw some interesting gradients. So, various tools that we were using spanned some of these scales. None of them really spanned all of them. So you had to basically do some leapfrogging to get from here, to take some knowledge you got from here and convincingly apply it in a model that would give you an answer at this scale. But at each stage, you could kind of check what you were doing using the measurement system most appropriate to that scale. So we hammered all this out over years of argument and discussion, and it worked out quite well. Here's one site. This is on a fen site, which is like a bog in the southern study area in Saskatchewan. I want you to imagine you're looking through a haze of mosquitoes at this. We're doing a low flyby over the site. This area, if you stepped off this walkway back then, you would sink up to your knees or your hips in black slime. And then shortly after that, it dried out completely. A few years later, it dried out completely. You could walk across it and maybe even play golf on it. And I think it got wet again. But things change there all the time. In winter, it was minus 40. It got down to minus 40. I think the record that we experienced flying the aircraft out there was minus 47. That was the surface air temperature, which is really cold. You don't want to be licking any part of your aircraft at that time. You'll lose the skin off your tongue. But very, very cold. Yeah. Don't do that. Here's the towers. We had two kinds of towers. We had the hero tower, where you go up the outside, it's a long, thin thing, and you hang off the outside. This is about 100 foot high. And this is for was due to his son, I think. He was part of the Harvard crew. And eddy correlation instruments and radiation instruments hanging off it above the canopy. And then we had these other rather nice scaffolding towers, and that is Joe Berry, I think, standing there. And he's sampling leaf physiology. And it's nice when you're getting up close and personal with your vegetation to be able to stand there and not worry about fooling off and do the work. Airborne eddy correlation. The masters of this were at the time the Canadians, a group led by Ray Desjardins and Peter Schwepp in Canada, the National Research Council of Canada. And they had this twin otter aircraft, which they started flying in 1982 and equipping with airborne eddy correlation in 1982. It is still flying. We have second generation of air crew going through it. I think the children of the first air crew are still involved in working this thing. And this is the little gust probe coming out the front here, which measures the updrafts and downdrafts of wind and also CO2 concentration, water vapor density, and temperatures. So these guys this guy would typically fly very low over the forest, about 20 foot above the surface, and could give you a map of the surface fluxes of CO2 and of water and heat. And recently, they're doing it with methane. So it's a wonderful tool, and they're still the world leaders. You know, here we are 30 years later, and they're really the group that still knows how to do this. We've been begging various institutions in the US to step up to do as good a job. There's Alan Betts. The reason I show this picture is Alan is a meteorologist who was loved to work with the European Centre for Medium-Range Weather Forecasting, which at the time was the best forecast model in the world. And we had this very intimate relationship with them, where Alan would look at our data, you know, almost on a daily basis coming out of the experiment, and talk to the guys over in Europe and tell them how bad or good they were doing. For example, one day their one-day forecast was off by 15 degrees centigrade for surface air temperature where we were working in Saskatchewan. And the reason for that was that it was wintertime, and the European model basically treated any snow-covered area in the Northern Hemisphere as like an open field covered with white snow. Whereas, you know, for the boreal forest and large chunks of the world, there's stuff sticking up through the snow, trees, which form very effective radiation traps, particularly at low solar angles. If you're walking through a forest in winter with a low solar angle, you know, just try looking along the path of the sun's rays, and basically what you'll see is black, all the trunks, very effective radiation trap. And this made a difference of 15 degrees centigrade in the calculated temperature for the area. So once they fixed that, terrific, better forecasts. Running the whole thing out of a our little Snowdrifters Lodge. And the operations. Here we are. We got, sites in the south, 4 or 6 towers, 3 or 4 towers in the north, helicopters, range of aircraft, all of the satellite stuff, and we would switch these aircraft from one site to another, the 600 kilometers, whenever we needed to. If the weather was good at one place, off we'd go. We were very much forecast driven, but that was a flexible way to get all the data, was basically move our little air fleet around as required. And here's the helicopter making a 600 kilometer trip from one site to the other. Basically took them all day. Okay, so what did we get out of all this? A whole lot of integrated data sets, and these haven't been just used by the people who were in the experiments, who were selected to do the experiments. We made a real effort to try and make it so that you didn't have to have been at the experiment to be able to use the data. So the data's been archived and documented so that you guys could go along and look it up if you wanted to. You could go and dig in there and look at any of these very rich data sets collected at vast expense, and they have been mined significantly since then. It was interesting to watch how people's thinking evolved as well during the experiment. We saw these different sort of little tsunamis of publications come out after each experiment. First of all, each PI would figure out their own data and would write a publication saying, well, this is what I did. I collected these data and this is what it means to me. And this is what I got out of it. This is what I learned. And then later, people would start taking these processed, cleaned up data sets that the collecting PIs had put together and meshing and merging them in interdisciplinary modeling and analysis. That took a lot of effort. But that was really the true yield, I think, of these experiments, was that they brought data from different disciplines together to give you the answers you needed. And people still using this stuff. And, these, I think, publications, publication rates, and number of people per year using the data sets. The data's still being used. And this slide is out of date, but it makes the point, I think, that people were using the data here in 2008 from both experiments, even though, Boris basically finished operations in 1996, and 5 finished operations in 1990. So very long-lived data sets. So what do you get out of all this? What was the point? We started out in the early mid-80s saying we need to have these integrated data sets if we're going to improve things. And we actually went and did it. We need the data from subsoil to orbit, and we actually went out and collected all those data. And the scientific community basically designed these experiments themselves to satisfy their own needs, to satisfy their own goals, which is improve the models and make better use of the satellite data. So out of that, we did get better land surface parameterizations, which have since integrated physiology and carbon exchange in a realistic way. We put these in the climate models. They work. And also, that's one set of activities, which is just the model improvement. Another set of activities was scaling up these process models to the global scale using satellite data. So that was done also as a direct result of this work. And, bottom line is we got better, more credible third generation climate models, which are going to be more used for global change prediction, and they already are delivering. Give you an example from work we did. This is with Jim Tucker and friends. Vegetation maps. Here's a 1 by 1 degree resolution. It's based on his AVHRR data. This is what it looks like at climate model resolutions. It was back then in the early 1990s, 4 by 5 degree resolution. Pretty chunky, huh? Some people were using it at 7 by 9 degree resolution. Some of the early GIS runs were using data at this kind of resolution. Generally speaking, most global models now are somewhere between these two resolutions. Climate models are closer now to 100 kilometer spatial resolution than they are to this. So the world of modeling is trending more and more to this kind of picture, the top picture. But as a result of all that work, we found ways to calculate FPAR, and not very well first time around, but at least we did it based on some kind of physical principles, something that was testable. FPAR fields that could go in the models, which we used to calculate transpiration, which was used to calculate NPP, and then also used to calculate carbon dioxide concentrations in the planetary boundary layer. This is work done by Scott Denning. You guys probably know. So, short story of how something evolved, what came out of it all. In a 20-year period, we went from a situation where the models were just awful to where the models were much better. We found a way to use the satellite data. We found a way to get people to work together. The experiments were a real driver for getting people together to develop new models and techniques, helped push along EOS, but I honestly believe that the best product of the whole business was the new generation of experienced, motivated students that came out of it, a lot of whom are around and now kind of influencing the field and taking it to greater heights. So a lot of effort by many people, but definitely worthwhile. So where does that leave you guys? I think it leaves you in a really good position to take this the next stage forward, which is making the models more realistic, more reliable, and more able to ingest and utilize the satellite data. Huge challenges ahead. People are going to be looking to you to answer their questions, their biggest fears about global change over the next 20 to 50 years. And it's going to be up to this very small community of people, you lot, basically, to come up with the answers. So that's really all the stuff that I wanted to talk about, in a one-way rant. I'd like to open up for discussion now for you guys to tell me what's on your mind.
Yeah.
Thank you very much, Piers. Can we open it up to questions in the room?
Sure. Whatever you want. Whatever works.
Questions, folks?
What perspective does being an astronaut give you for your earth science work?
I learned a thing or two from flying in space that I didn't think I would. One was that, I sort of intellectually knew that the atmosphere was pretty thin relative to the size of the Earth. But when you go up there and you see it for yourself, you think, holy moly, there's almost nothing there. It's like an onion skin. So you consider you have an Earth that's, 8,000 miles diameter, but an atmosphere that's really effectively only 25 miles to 30 miles thick. It's almost nothing. So when you're flying around the world and you look at the Earth's horizon, it's very, very thin. It really is. There's hardly anything there. And everything's flatter than you would expect. All the hurricanes are very, very wide, 1,000 kilometers wide, but very, very flat. They're almost like oil patterns moving around on the surface of water. They're so flat. The whole structure is only about 10 miles high, but it's 1,000 miles across. So everything's sort of thinner and flatter than you imagine. The other thing that really came through to me was how small the world is. If you're looking out the window of a spacecraft, look straight down, you can see rivers, you can see things, cities, quite recognizable, the layout of cities that you're familiar with. So you can see things that are, relate to you on a human scale that you're familiar with. But then you go around the whole planet seeing things at that scale, and it only takes you an hour and a half to do that. So the world is much smaller than subjectively, I think, us groundhuggers think it is. Not a very good place.
Can I ask you a question? Yeah. I have a question about the space station, Piers. So we had that space station up for several years now. What were the constraints?
Sorry about that.
It doesn't look like we really use the space station for Earth observation as much as we could have.
Can I call you back? Sorry about that. Business as usual. Well, it really took till 2010 to build space station. You know, there's interruptions when we lost Columbia in 2003, so it's like a 2.5-year halt on building. It really took a decade from 2000 to 2010 to actually build it. Now it's up there and running, and I was just talking to Don Pettit, who's spent 6 months on it and came back 3 weeks ago. I was talking to him the day before yesterday, and he says that at last we got the space station we dreamt of, and they've started to put experiments on it. Personally, I'm hoping we'll see a lot of external payloads on it over the next decade and a half. We've got a cloud and aerosol LiDAR going up next year. And it would be nice to see something like a Son of Jedi or whatever also mounted on there in the out years. So I think there's some opportunities there for Earth remote sensing from space station. And I'm hoping to push those along.
There are a few more questions in the chat room. One person follows on from your theme and your talk about what kinds of ecosystems should we focus our attention on post-Boreas and Fife.
Well, as you know, there was a big experiment in Amazonia that was looking basically at the effects of deforestation, among other things. But I think the focus over the next 10 to 20 years will be in the Arctic boreal zone again, because things are changing there so rapidly. Melting permafrost is changing the landscape in front of people's eyes, I mean, quite literally. And there's this possibility of large-scale releases of methane and carbon dioxide from the frozen carbon stores up there as they thaw out. And also, we're seeing drying and warming of the boreal forest itself. And Scott Getz calls it the browning of the boreal forest. It's getting browner globally. And we may see quite a large sort of migration of grassland systems into the southern part of what is now the boreal forest over the next few decades. So I think the rapid, important changes are going to be in this northern zone. We'll see.
I think we can dovetail that into a question Ranga asked in the chat room, which is are the good times for remote sensing behind us now with EOS having gaps and Landsat gaps, etc.?
God, I hope not. I'm really hoping that we've had a run of some hard times, if you like. There was a missed opportunity to basically sustain and continue EOS without breaks or hiccups, which I think was a missed opportunity. But now I think there's something of a recovery effort in place now, as people recognizing that we could really lose out on a sort of continuation of climate data. And people are focusing now on what does it take to put together a really solid climate data record based on satellite data. EOS gave us a wonderful starting place. Now we're trying to do the best we can using NPP and JPES sensors going forward. What else do we need to do? What other sensors can we bring to the field to do that? Now, another thing, though, I mean, you could take an upbeat view of this as well. When we started Fife, really all we had was Landsat, NOAA AVHRR, GOES, and a bit of Spot if we wanted to pay for it. And that was it. That was it for satellite remote sensing. It was really thin. We consider what we have now, you know, we're a lot better off, even though it's taken a bit of a dip. So I'm hoping for good things ahead.
So do you feel that Landsat is important to continue for successful Earth observations?
Yeah, I think it is. I think more to the point, there's scientific community that makes use of Landsat, but there's also a whole bunch of other communities that use those data, which is great. It's nice to have somebody else advocating it besides us. I would think that Landsat's an important instrument to our community, but there are other ones that I think are almost, as important, that are as important. The MODIS data record has just been fabulous for doing global studies. And I think we can continue to get more out of MODIS and VIIRS, hopefully, in the future. I don't know, what do you think, Ranga?
Can you hear me, Piers?
I can hear you, yeah.
Yeah, I was actually typing a question for you, which is compared to the earlier days, presently, there are a lot of activities sponsored by NASA, but these activities are kind of fractured. There's nothing like the IWG that we had in the earlier days. So there is, at least for me, there seems to be there's no visible community like it was in the earlier days, like when we had IWG. What are your thoughts on that?
I think that's valid, there was a lot of enthusiasm, and I think it was well-placed enthusiasm to bring the scientists together, the practicing scientists together, to discuss their science in a forum like the IWG, and a lot of good stuff came out of it. A lot of good thinking came out of it. And that kind of thinking influenced the stuff that I was talking about earlier, in terms of how do we work together to do better, to get at the answers we want. It became very apparent, I think, that no person had all the answers. You had to rely on other communities to help you out and get you what you needed. And I think you've raised a really good point. I see less of that now. I see more people doing their niche activities, which are fun for them, perhaps, but less collaborative efforts now than back then. Did everyone get tired? Maybe it's time to, I think it's probably about time to revive something like that. Good point.
Yes, very much. What I think is we lack leadership, in my personal opinion. And
well, we'll have to get out there and do it again, Ranga.
We're counting
So
on
next
you.
time we meet, we can talk about that.
We are very happy to have you back in science, obviously, and we are counting on you, hoping that you would play a leadership role and rallying the community again.
Well, I'm too old to do good science, so it's probably a good thing to do, yeah. I think there's a will there. It's just part of this, Ranga. It's interesting to see how institutions have evolved. I remember the IWG came together because of the big push-up to do EOS. How do we do EOS? What makes sense? What are the priorities? And that required that kind of effort. Probably the time is right to do it again, to do something like that again. Because right now, you're right, people are basically stovepiped into their little PI areas, and there's not much cross-collaboration. So, yeah. Okay, noted. I've got my marching orders.
Is it time for another ISIL-SCIP data? You had ISIL-SCIP 1 and 2, but we haven't had an update in quite a while.
That would be something really worth asking the modeling community. We had a modeling workshop the other day that was concentrating on model weaknesses for doing things in the Arctic boreal zone. But I don't think there's been an effort recently to figure out, hey, what kind of data sets would you like, versus what you have now. I don't it's been a while since an assessment like that has been made. You guys would know better than I do the last time that was done.
But those
And we tried to do that. The EOSCIP global data sets, we tried to take what we had learned in the field experiments and in all the satellite algorithm work and produce these standardized data sets, which, while they weren't perfect, they could be instantly used by modelers because they are wall-to-wall, no gaps, and user-friendly. You know, with promises, we'll try and improve them in the out years. So it might be worth revisiting that business.
A lot of the skip data sets were used for parameterizing or initializing the models, but we have a lot more variables now to actually test the performance of the models themselves, like the energy and water budgets and all that stuff. So I think probably there is a need for something like that, not only for initializing and parameterizing the models, but also testing the performance of the models.
You know, I don't. When was the last time the community sat down and said, "This is what we need. What can you give us?" I'm not sure. It's been a while since we had that conversation.
Yeah.
We certainly did that for EOSCIP 1 and 2.
Yeah.
We went to the modeling community and said, "Hey, you know, what would you really like?" And they were very frank about what they wanted. What they didn't want was to have to do all the processing themselves. What they wanted was our best guess, our best shot at the parameters. You know, when I say our, I mean the remote sensing community. They wanted the remote sensing community to give their best shot at global parameter sets for them to use, rather than just sort of, you know, go up to them with a dump truck of level 0 data and say, "Hey, here's some algorithms. Go and sort it out yourself."
Yeah.
So that was the result of that conversation, and we did give them something which got used. I'm not sure when the last time that conversation took place. It's been a while, I think.
Someone from the chat room puts in a plug for studying the Himalayas. He or she says they're the least studied and says they're as important as the Amazon and Boreas, and asks if you have any interest in developing LSMs for the Himalayas.
Well, I'm trying to think that the problems with the mountains are very different from, you know, the large biomes. There's the whole business of airflows around them. I mean, without the Himalayas, you wouldn't have the monsoon, because it acts as a wall, you know, a dam against flow coming in from the surrounding oceans. So we've got better and better at representing the effects of mountain ranges in models by using higher and higher resolution models, so we can actually kind of see the mountains as they really are, as opposed to big cubey type blocks, you know, that are one by 1 degree and maybe 5 kilometers high. So we're doing a better job on that. The energy balance and radiation balance of mountain ranges is not such a tough prospect. I'm waiting for Ranga to correct me on that, but I think that the business of the energy budget calculations for these places is not too tough. It's snow or rock for the most part, and it's fairly straightforward to model compared to, for example, the Amazon or the boreal forest, which has got lots of complicated vegetation doing all kinds of things all over it. But I'd love to go and study the Himalayas because it gives me an excuse to go there.
Well, I think we've unfortunately run out of time. We're going to move on to our next talk, but we'd really like to thank you very much for joining us today, and for all the people out on the internet listening. Thanks a lot.